This video is an introduction to the course Engineering Mechanics Dynamics. This course continues from the previous course Engineering Mechanics Statics. Therefore, you are expected to have solid foundation in statics. And if that is not the case, I strongly encourage you to review statics before starting this course. Just like what we did in the course of statics, in this course, we continue to study how rigid, non-deformable bodies react to forces acting on them. In statics, we focus on bodies that are in equilibrium. In other words, bodies that are either at rest or moving at a constant speed in the same direction, although our study objects are almost always at rest. In statics, the governing law is Newton's first law, that the resultant force vector acting on the body is zero. Now, in dynamics course, as you probably guessed, we study bodies that are in motion. There are two parts under this subject. The first part is called kinematics, in which we are only concerned with the geometric aspects of motion, the displacement, the velocity, the acceleration, all as functions of time. Kinematics doesn't study how motion is caused by the forces acting on the object. As you probably learned in physics, displacement is the change in position of the object as time changes, and velocity is the time derivative of displacement, and the acceleration is the time derivative of velocity. I need to point out that displacement, velocity, and acceleration are all vectors, but here they are shown as scalars for simplification reasons. And an example of a kinematic problem could be to determine at what height and at what velocity the hitter should expect to hit the ball if the initial position and velocity of the ball are known. We could even predict the trajectory of the ball. Once again, we are only interested in the geometry of the motion, not the driving forces. The second part of dynamics is called kinetics, and it studies how motion is resulted from external forces acting on the object. The governing law is Newton's second law, that the resultant force acting on the body equals to the mass of the body times its acceleration. And here is how this course is structured. We will start with particle kinematics, and then move on to particle kinetics, which includes force and acceleration based on Newton's second law, and then work and energy, and lastly, impulse and momentum. And then we will follow the same order to study rigid body planar motion, starting with rigid body kinematics, and then rigid body kinetics, which again includes force and acceleration, work and energy, and impulse and momentum. As we move along with this course, it might seem to you that this course covers a lot of topics with a large number of formulas to study. It could be overwhelming. Therefore, I'd like to point out to you that, in my opinion, there are only 4 most fundamental formulas that you definitely should know by heart. The 2 kinematic equations that relate displacement, velocity, and acceleration to time, Newton's second law, and lastly, the equation that relates the length of an arc to its central angle. Note that, again, only scalar equations are shown here and from here on to simplify the demonstration. We will learn the proper vector formulations later. The reason why I said I think these are the only 4 most fundamental formulas in this class is because most other formulas in this class can be derived from these 4. For example, if you combine these 2 equations by canceling out dt, then you get the third kinematic equation. If you take this newly derived equation, combine it with Newton's second law, integrate, you will get this equation, which is the principle of work and energy. If you combine these two and then integrate, you can get this equation, which is the principle of linear impulse and momentum. And if you add in the fourth equation, combine all of them, you can derive a series of formulas that involve rotational motion, such as angular velocity, angular acceleration, angular kinematics, how moment causes angular acceleration, work of moment, principle of angular impulse and momentum, and etc. So my advice to you is that when you study dynamics, don't get caught up in memorizing so many formulas. That is not the most efficient way to learn dynamics. More importantly, you need to focus on understanding the fundamental relationships between different physical quantities and also how to apply your mathematical skills to derive these relationships.